Okay, thank you very much. So first of all, I guess you know this lecture will be in English, but only because I'm 1 year too young. If I was 1 year older, I would take Russian in class and I would now speak fluently, but unfortunately, that's the case. So this lecture is about computational social choice, and this is something on the mixture of more or less theory of voting, theory of making choices, and computers. But before we start, so I have to tell you a few things about how I teach. So this, I'm not even supposed to teach you or just show you things, but essentially I was told that anyone can come here and anyone will. But when I teach my class in Kraków, in Poland, I teach Introduction to Complexity Theory, I teach algorithms, and I have a plush Angry Bird toy. I throw it at the students, and whoever catches it becomes Harold. And I say, Harold, do you like this proof? Or what should be next in the equation? So I did not bring Harold today, don't worry. But I do expect that you will speak. So let's make a test. How many of you can speak? 1, 2, yeah, increasing. See, at the beginning, no one knew how to speak, but I've already taught you to speak all. How successful? Okay, very good. Okay, so first, what is computational social choice? It's a relatively large field and relatively young. The earliest papers on this topic started in late 80s, early 90s. Essentially, it's about collective decision making. So a group wants to make a decision together, somehow taking all preferences into account, and it incorporates voting. So this is essentially the focus of this 5-lecture course. But there's also things like judgment aggregation. This is actually something that can happen in a court. So imagine that there can be a court case, and for example, there's a car that was speeding, and you can have in the court some people can say, you know, I saw this car speeding, or I saw a car speeding, and this was this car. Therefore, it should get a ticket. So some juries would say, yes, I saw the car speeding, but I don't know if it was this car. Others will say, it was this car, but it was not speeding. Some will say all of these things. And you have a bunch of preferences. And it turned out that, in fact, in real cases in courts, when you aggregated these preferences, depending on whether you aggregate conclusions or premises, the person actually gets a ticket or not. So there were actually real court cases that spawned this whole area of research. And this is all we will talk about it right now, because the focus is voting. There are also things like fair allocation. So for example, if you go to a website Splitit.com, you can actually, for example, find good ways of sharing rent with roommates, or fair ways of sharing fares for taxis, things like that. There are actually algorithms for fair splitting of things. Again, nothing that we'll do here. Matching under preferences. Again, if your child goes to school and maybe you have some preferences on which school the child goes to, and the school has some preferences, for example, is this child doing well in school or not, you still have to match students to schools, and this is what's done. And generally cooperative games. So essentially, this whole area is about whatever we can do together. But as I said, the focus is of this particular class is voting. And so I guess we will not really see much in terms of titles of the slides, which I guess is fine. In fact, when I was 18 and I was first taken for a military checkup, for some reason there was a psychiatrist asking us, and he asked, what does your father do? I said, he's a teacher. What does he teach? I don't know. It's something about electronics. And so the doctor asked, but you don't know the titles of the courses? No, but I know the contents, and that's what matters. Oh, that's what you think. I said so, so indeed, that's what I think. And then it turned out that psychiatrists are not very mentally stable. So he just started shouting at me. But I was in consequence, I was never in the military. So that's good. There's a book called Computational Social Choice. This is a collective work. It's kind of scientific but accessible. Collective work by essentially more or less everyone who matters in computational social choice. It's easily available on the web. It is for free. It was meant to be for free. You can buy paper copy if you somehow like to spend money, but the PDF is available. There's also a more researchy book also for free, which is Trends in Computational Social Choice. And there's a bunch of survey papers, and there'll be actually a bunch of titles of papers showing up on these slides. I will not really comment on them much. And in this book, at least the first 10 chapters focus on voting. So that's why I feel it's okay if it's a course about computational social choice and I speak of voting only. Okay, so then why are elections important? One of the first answers is always politics. You know, choosing leaders, choosing presidents, finding parliaments, whatever else. Of course, politicians don't care about what we do, and we try to not care about what politicians do. So really, this is a really convenient, somehow, we pretend we're discussing politics, but we really actually don't care about it. So everyone understands how political decisions work. But in fact, we believe that these algorithms for elections and discussions of voting actually matter because there are many other settings beyond politics where this is important. So in the business settings, stockholders can make decisions in companies, university senates make hiring decisions, there are competitions. So for example, if you know Eurovision Song Contest, there's a bunch of songs that compete, various countries vote, and then eventually some song wins. There are ways in which one can run such a contest, or if you take Formula 1 racing, then each race is actually, we will soon see that each race is an election. Oh, sorry, each race is a vote, and together the World Championship is an election, and lots of this theory applies. And technically, this is all applicable to generally multi-agent systems. This is also where this theory of voting is usually published. So multi-agent because there are different entities that have preferences that they can act together. You're welcome to join. So as I told everyone, this lecture is meant to be extremely informal. So in particular, if there's someone who wants to ask a question, please do. If there's someone who says, I don't actually understand, can you repeat? Fine, do it. So my purpose here is actually to pass some knowledge. So in particular, I don't care if I go only through half of the material I prepared. I care if you understand. Okay. So essentially, elections are things about aggregating opinions. And that's what we will do.
Do you differentiate between opinions, judgments, preferences?
Not really. So that's, you would need a philosopher for that. So, I mean, and I'm serious. These people actually do discuss such things. Here, you will very soon see that when I say preferences, opinions, votes, it's the same thing, and it's a relatively primitive mathematical notion. So we're kind of at the level of people who get things dirty rather than who think too much about this thing. Okay, so computational social choice and voting. The first thing we'll start is, what is the election formalism? So when you study graph theory, graphs are not nice pictures on the board. Graphs are actually some sort of algebraic notions. And the same is true in elections. And there are two kinds of elections, ordinal and approval. Today we'll be essentially talking about ordinal only. And the way it works is as follows. So we have formal setting. An election is simply a pair where an E with a set of candidates and set of voters. So set of candidates is, for example, the red guy, orange, pink, blue, and green. And thanks to my co-author Nimrod Talmon, who once was giving a similar lecture and confused the colors of orange and green, since then there's not a single lecture when I did not confuse colors. So correct me if I say something wrong. Okay, we're also assuming we have a set of voters. So here you can see that this is actual set. This is technically a collection, which means that technically voters have names and have identities, and someone could look up who the actual voter is in almost all voting rules, this is ignored. But there are cases where it matters, so we keep it as well. And this is how our preferences look like. So we're simply assuming that for every voter, like for V1, we have a strict linear order over the candidates. So the red guy is the most preferred, then the orange guy, pink, blue, and green. And as you notice, this formalism does not allow to express intensity of preferences. So you're simply allowed to say, this guy is best, this is worst, these guys are in the middle, but you cannot say, this guy is absolutely great, this guy is okay, all the rest, nonsense. So this is, you can't do that, and yeah, you look like you have a question. Create one. Yeah, okay. So this is a basic formalism used usually in economics. You can also clearly see, for example, why this is completely inapplicable to, say, elections of parliament. In last parliamentary election in Poland, there were 8,000 candidates. So it would take a while to create a ranking. In presidential elections, it's a bit easier. There's maybe 10 candidates at most. So then you can do it. And there are also countries like, say, Australia, which uses a system called STV, which we'll soon see, where they actually are expected to rank candidates, but they have smaller sets, and they can also say, I like party A. I want to go with the ranking that party A says. But still, it's somehow assumed that in our heads we have these preferences, somehow we can have them. Hello, come in. So actually, I have to tell you about other thing I do in my classes, which I will, of course, not do in this class as well, but it's a lot of fun. In my complexity class, I have a piggy bank. It's actually in the shape of a sheep. It's a very nice sheep, which I put in front of the class. When students come late, they actually put coins in. And after the class, so the class takes 2 semesters, so after a year, we go together with the students to have beer. So I certainly hope that my bosses do not watch these movies as we're being recorded. Actually, some of them don't. Okay, so this is our basic model. We're also assuming we have a voting rule, which means it's a function that simply accepts, this is called preference profile. So for every voter, we know the preferences, and we're returning a set of tied winners. And of course, you could say that if we have an election, I would like to have a single winner. Even though it would be a bit embarrassing if the election said, you know, we're running for president, and this guy and this guy could be presidents. What do we do? But for mathematical formalism, of course, sometimes we actually do assume that we have rules that produce a single winner. And if there's a tie, they break it, for example, lexicographically on the names of the candidates. But for mathematical studies, often it's better to assume that you have a whole set of tied winners, of which each is as good, because you can imagine that this is completely symmetric. So I can pretend I can write on the blackboard. So if, oh, not here, I guess. If you have preference profile like A, B, C, then A, C, B, B, A, C, B, C, A, and C, A, B, C, B, A, there's full symmetry. And there's absolutely nothing you can do. Then you would have to say everyone wins, or you would somehow artificially have to break the tie. So we're simply saying that the tie breaking is done sometime later, we don't care. In practice, it is, in the end, in almost all legal systems, in the end, there's a coin toss. Or saying something like the older guy or whoever wins. Okay, now examples of voting rules. Okay, before I show you the actual examples, you see the preferences, you understand them by now. I want at least a few voices who should win and why. So in this case, so usually when I do this, everyone can win, but not in this case. Here some people are clearly better than others, but still. Some suggestions, who should win and why. And of course, if, yeah.
I think the academic guy should win.
Oh, the red one?
Yeah, the red
Yeah, okay, why?
Well, first, he won 2 first places.
Yeah.
And his other places are not too far from
Yeah, you could argue he's kind of average or below, but he has two first press. Someone said green. Was it you?
Yes, it was me.
Why? Why green?
Green is good enough for most of voters.
Good point. She is good enough for nearly all, not all, but nearly all. Other ideas?
Depends on the rule.
So in fact, the pink lady is not so bad as well. She has 2 first places. Here, okay, not great. Here she's kind of hated. But in fact, if you run plurality rule, which means you associate, so a big family of voting rules actually just simply associates points with positions. Plurality rule is what is used in almost every country in presidential elections, except that there are some twists at the end sometimes. Just 1 point for being first. It means red and pink are tied. So good 1 point for whoever said red. For you. A border rule. You could also say...
Sorry, can you please explain what tied means when applied to winners?
Sure. So in this case, the red guy gets 1, 2 points, right? The pink lady gets 1, 2, 2 points. They have we're choosing people with the highest number of points, so they're both tied as winners. Which means that according to this rule, both him and her can be winners. So essentially the rule says these are equally good. I have no evidence to decide otherwise. So to make final choice, you have to do it yourself. So you could say that P is before red, before R, so pink wins. Or you could say, there's 2 of them, let's throw a coin. Whichever one side comes, red goes, if another side, the pink goes. Or you could say, let's choose a random voter, maybe this one. Oh, he thinks red is better than pink. Choose red. There are so in practice, so here we're assuming that somehow in the end only one of them is actual winner. But this is the set that the rule says they're equally good and best. So are you satisfied with the answer?
Yes, thank you.
Yes, sure. Sometimes I also ask, are you satisfied with the answer, or did you learn more than you wished? And actually once a student said yes. That was embarrassing then. Okay, the next rule is border rule. So this is actually something you can associate with contests. So if you look at, in the older days, in Formula 1 racing, actually these days as well, in Formula 1 racing, the top position gets some highest score, then some lower score, and so on. If we're using the basic linear scheme, so essentially this guy is first and he's better than 4 people, so he gets 4 points here, 4 plus 2 plus 2 plus 1 plus 2 plus 4. And if you sum up these scores, it turns out that both red and green are winning. Okay? You can have a rule such as K approval, which is actually a bit of a silly rule because it says that for 2 first, in this case you just choose the K. In this case I chose 2, so 2 first places get points. It's a bit silly because if everyone thought that red is best and, for example, green is second best, still they would be tied, even though everyone clearly thought that red was superior. But so be it. There's a rule called veto, not really used in practice. Here red wins because he's never last. And there can be also completely different ideas of how to make a choice. So there's a notion of a Condorcet winner and of a so-called majority graph. So you can put these guys as nodes in a graph. And now if you look at the green lady, we can say she's defeating the red guy because, so here it's red defeats green. It happens once, but then 4 votes where green is defeating red, and only 1 more where red is defeating green. So green is winning 4-2. So we're showing she's defeating him. And if you actually look, she has a majority over everyone, and therefore she's declared as Condorcet winner. So is it clear to everyone that Condorcet winner may not always exist? Okay, it's clear to one person. Is it clear to someone who's willing to say yes?
Yes.
Okay, but one repeats?
In your example.
Yeah, exactly, exactly. And one could make even a shorter one with just 3 votes that are symmetrically shifted. Yes, so Condorcet winner doesn't always exist, but we can make its full graph. And for example, we can use something called Copeland rule, where we're simply saying you get 1 point for whoever is defeated by you. And for example, you get half a point for a tie, and then just in this case, the green lady would have 1, 2, 3, 4 points, whereas the red guy would have 3 because he's only winning 3 times. The poor orange guy would only, they are tying, so maybe he would have half a point. But otherwise, one more tie, nice. Okay? And there's essentially a rule is called Condorcet consistent if it guarantees that a Condorcet winner wins if there is one, and it does something similar otherwise. So here we actually have the points. Okay, there's a bunch of these Condorcet consistent rules, and I will tell you a bit more about some of them later. And finally, rule that we'll get to in the second part of this course more, STV. And this is actually plurality and STV are one of the few of these things that are actually really used in practice. Also, plurality because it's probably the worst rule, and STV is actually surprising in some ways. But the way STV works is as follows. We look at the top places. So 2 people have 2 points, but nobody has a strict majority. Therefore, we proceed as follows. If nobody has a strict majority, we're removing from the election whoever has fewest votes, which means that this rule will not like the green lady very much because she has no first places, which means she has to be removed in the first round. And still, nothing changed on the first position because she was never there. So we still have to remove whoever has fewest first places. So we have a choice between blue and orange. Again, we somehow have to make this choice. In this case, let's toss a coin and remove orange. Okay, now red has 1, 2, 3 points. Blue has 1, pink has 2. So blue has to be removed. And now there's a majority support for the red guy, and so he wins. So this is actually really used in Australia, in Ireland, in few places. This rule has some strange features. I will show you an actual example much later on. But under this rule, it's possible that if someone actually improves his position in the preference ranking, and he was winning before, he can stop winning. So it means if you're running a political campaign to promote yourself, you can actually prevent yourself from winning if you're too successful. And this actually happened once in Australia. One of the parties realized that given the polls, it's likely to win some number of seats in the parliament, but if too many of its supporters vote for it, it will actually get 1 less. So they had a bit of a tough time how to explain to the voters, please vote for us, but only a little bit. And this rarely happens in practice, but it has. And actually such situations often happen, sometimes happen. So for example, I think in South Korea, once some popular musician tweeted, "I will vote for this guy." All of a sudden, a bunch of 20-year-olds went to vote. The result of election was a complete unexpected mess because all of a sudden, a huge number of voters that never before turned up to the voting place actually voted how the musician said. So there are funny things that can happen with elections. Okay, so I told you that Formula 1 is actually, why do these things actually matter? Why did we go through so many voting rules? So I told you that Formula 1 can be seen as an election of its own. So it's season 2008. So I didn't make this choice because there was a Polish driver, who apparently is again. I made this choice because this is what my student prepared, and that's what I have. And here, as you know, so in Formula 1 racing, after each race, so each driver finishes at a given position, which means that each race gives us a ranking exactly like this. Whoever is first, whoever is second, and so on. And even more nicely, I'm maybe going to, under Formula 1, you have a number of points associated with each of these. So currently, I think it's maybe 25 for the first place and something else for the others, decreasing, of course. In 2008, when we were looking at this table, it was somehow smaller because there's about 20 races, and this guy has 98 points. Yeah?
What is kierowca?
Oh, sorry, that's driver. So here, Lewis Hamilton was a world champion with 98 points, and these are positions in races that he got. Then Felipe Massa was 97, just 1 point. Isn't that disappointing when you're Felipe Massa? And so on. So the official ranking is like that. But if you used Borda, all of a sudden Felipe Massa would be actually doing much worse. But the Polish driver, not so bad. So simply by changing the voting rule. If we use plurality, all of a sudden Felipe Massa is a world champion now, because he won 6 races and Lewis Hamilton only got 5. If we use 2 approval, 3 approval, and so on, they start tying. They were pretty good both. If we use Copeland election, again, we have a switch. All of a sudden, Felipe Massa was closer to being a world champion than Hamilton. Unless we use a strange rule called Maximin, then he's 9th, but the Polish guy is 1st, so okay, maybe not such a bad rule. And again, for STV, we have a switch. So as you can see, actually, whoever was a world champion in Formula 1 in 2008 actually is pretty darn arbitrary. Because you can choose the voting rule however you please, and you can set up things the way you like. Okay, so this is sometimes one of the most convincing slides for people why elections matter. Because things that don't matter, like Formula 1, depend on it. Okay, the problem is that there's something called Arrow's theorem. It is a formal statement, which I'm not giving here, but it essentially said that there is no perfect, always fair voting rule. Simply such a thing does not exist. Except for one, dictatorship. But most people don't think it's fair. So we will not prove Arrow's theorem. We will actually prove something else that is related. But conclusion is that voting rules are designed for specific purposes. You have to understand them, and you need to choose one for a particular purpose, but they will always at least have some flaws. Okay, so what we've seen so far is computational social choice. We have 2 formalism here, but we focus on ordinal. There are scoring rules, such as Formula 1. Other ideas like this iterative STV, or the graph thing like Condorcet rules.
Sorry.
Yeah.
Does STV has any, what does the abbreviation stand for?
Oh, sorry, I should have said. It's a single transferable vote. Because plurality in some settings, usually when we elect more people than one, is called single non-transferable vote, which means I vote for you, you get this vote, and that's it. It cannot move. But under STV, I vote for you, but if you're removed, then I move my vote there, there, and there. So this is what it stands for, sorry. Okay, we have plurality, Borda, approval rules, and a bunch of other things. And there are committee elections, the things when you choose a group of people. This is the second part of the course, and probably the last 2 lectures, or maybe last 2 or 3 lectures, in other words, tomorrow. But we're focusing on single winner rules, like here. And what do we care about when we think about single winner rules from the point of view of computational social choice? Well, the first thing is winner determination. So it seems kind of intuitive that if you have the election, it would be pretty nice if there was a polynomial time algorithm to compute it. And in most cases, there is, except when there's none. And so here normally I would start discussing a certain voting rule, but I realized that actually I don't know how much do you know about computational complexity theory. Of course, if for some reason you feel like taking responsibility for everyone in the class and saying, we actually know these things, move on, then please do. I guess you're maybe one of the only persons who could. But otherwise, I'll have like 5 slides about complexity theory. Okay. So first of all, what does it mean that a problem is computationally hard? So we somehow agreed in computer science that a problem is easy if there is a polynomial time algorithm. This is, of course, just a workaround, because if the running time is n to the power of 100, it's a polynomial, just fine, but it's not very practical. And of course, you can say n to the 100 never happens, but when they showed a first algorithm to recognize if a number is prime, the running time was something like n to the 12th. Of course, everything in big O notation. And that means that, you care if a number is prime if it has maybe 100, 200, 500 digits. Not very useful. But still, polynomial time is what we think is an easy problem. So if there's no polynomial time algorithm, then you could say, okay, this is evidence, this is really hard. The problem is that even though we can prove that such problems exist, so for example, the problem of checking if a given algorithm completes its time within 2 to the power of n steps requires exactly 2 to the power of n steps. Because, if you haven't taken a course on basic computability theory, then please do. Because you will learn there things such as the only way to predict future is by waiting for it to happen. And this is a time hierarchy theorem, which essentially says that the only way to simulate a program is to execute all its steps. So if we're asking what will happen after exponential number of steps, we have to make them all. But this is not really useful for almost all problems that you encounter in basic computer science, because what we really care about is the class NP. So you can see I have some affinity for strange drawings, but the class NP is actually what we care about. And this is something called, NP stands for non-deterministic polynomial, and it means we're going to run an algorithm that is non-deterministic, which means it can make guesses, and it has to make polynomial number of steps, but somehow assuming the guesses are correct. And it's best to describe it when we look at what's deterministic and what's non-deterministic. So if we have a deterministic computation, we start with some input x, and the algorithm makes step by step by step some computation, and eventually we're mostly, this theory of complexity is mostly dealing with decision problems. So in the end, you have to say yes or no. So maybe the question is this guy a winner of the election? Yes or no? Or does this graph have a bridge? Yes or no? Or is this graph connected? Yes or no? So we make sequence of steps. We have an answer. I guess most of you write programs. You know exactly what it is. Now, non-deterministic computation starts with input, then it makes a step. Okay, this one was deterministic. And then it realizes it has two choices. So I can go maybe one way or other way. And one of these ways, for example, ends with no. Then on the other one, I have more choices. And eventually, I have a whole path, whole tree of computation, where if there is a path that leads to the answer yes, then I claim that this computation answered yes. Okay, does anyone have a favorite difficult NP problem? I guess you might have one, but maybe someone else. Okay, let's use the kind of the traveling salesman problem. In the traveling salesman problem, you have a number of cities. For each city, you have a cost of traveling from one to the other, and the same cost for going back. Your job is to find a cycle that goes through all the cities for each exactly once. And in a decision variant of the problem, the cost has to be below some given threshold. So if you try to do it deterministically, you will end up probably coming up with exponential time algorithm. So if you don't think much, you will simply try n factorial. If n is the number of cities, n factorial possibilities. If you think heavily, then you will come up with a dynamic program with 2 to the power of n steps and this much, and the same usage of memory. And that's it, at least so far. But if you have a non-deterministic machine, then in your first set of guesses, you can say, okay, I start from city number 1. Now, let me guess which city I'm going to next. And you'll have n-1 possible choices. You'll go through one of them. And the fact that it's non-deterministic and it somehow wants you to go to yes answer, then you will go the right way. And then you can guess the next city, the next city, the next city, and so on. And in the end, you will have to verify that the cycle you found has a given cost. Okay? So this is what non-deterministic computation is. And of course, in polynomial time deterministic, we care that there's a polynomial number of steps. In non-deterministic polynomial computation, we care that this tree has polynomial number of steps. So again, you're making polynomially many steps, but you're allowed to guess. This is NP. Okay. So another example of a problem from NP is set cover. So here you're given some items, like here numbers 1, 2, 3, 4, 5, 6. You're given some sets. And the question is there a family of K sets? K is also part of the input from S whose union is equal to the union of all sets from S. So if K is equal to 2, in this case, it's, again, your algorithm for each set, your algorithm can non-deterministically guess, is this set in or not? So for example, for the blue, you would say yes. For the yellow, you would say no. And maybe for the red, you would say yes. And then you check, you verify that there is an answer. So complexity class NP, you can say this is whatever you can compute in non-deterministic polynomial time. This is what complexity theorists like and use. If you're a normal person and you simply want to use this class to learn about problems you have, this is class of problems whose solutions can be verified in deterministic polynomial time. Because for whatever problem you have, by this non-deterministic nature of computation, you can guess what the solution is, and then all it takes, you just have to verify that it is correct. So essentially, NP is the class of problems for which it is possible to verify the solution. Okay, who's so far happy with this explanation? 1, 2, well, more than 3. This is many. Okay, very good. Okay, so we have explained what NP is. We also need what is NP complete. And to this end, the problem is that no one knows if P equals NP. And some people would say that NP is this class where we can verify answers. So maybe if P was equal to NP, then there would be an easy way to verify the proof that P is equal to NP, and we could do it, and we haven't done it for the last 30 or 40 years, so therefore they must be different. This is of course not a formal argument. Some people simply say that. But so far, essentially, pretty much everyone in computer science believes that P is different from NP, and there is no proof. And so if you prove that P is equal to NP, or P is not equal to NP, then you get $1 million from Clay Math Foundation. Of course, if you prove P is not equal to NP, publish the paper, claim your money. If you prove that P is equal to NP, hide wherever you can, because all secret agencies of the world will be after you, because it means you can break every single code. But more importantly, you can break every single code, so steal from all the banks you can. And it's much more than 1 million. Only then publish. Okay. We don't know if these classes are equal or not, but we believe they're not equal. And we need a partial order of hardness on problems to actually be able to somehow say that certain things are in NP but not in P, provided that P is not equal to NP. And what we use is reductions between problems. Okay? The formal setting is that we have two decision problems. So a decision problem is something where simply you have some input and you have a question, yes, no question. Like this set cover thing where you ask, can I choose up to K sets that cover everything or things like that. Okay, I'm somehow really missing my Harold toy. I really would like to talk with someone, but I'm restraining myself. Okay, and we're saying A reduces to B if there's a polynomial time function f such that this happens. And this is very nice, but a picture is even nicer. So it means that, so here we have problems with answer yes from problem A. So instances with answer yes. Here we have instances with answer no. And a reduction translates an input from one type of the problem to the other, such that it maintains the answer. So if the answer was no, the answer has to be no. The answer is yes, the answer still stays yes. So the way I teach it in my complexity class, so I was surprised, but apparently, so I thought that I'm old enough and that I've watched all these somehow kung fu movies that were popular in the 80s and 90s, and they didn't. But actually, apparently, there was a number of remakes recently. So in a typical kung fu movie, you have this young, usually somehow American guy, who, for example, travels to China, and he's, I don't know, he has trouble in the world, but he finds this really smart Chinese master. So the young guy sits there and is in trouble, and the Chinese master is sitting there just doing nothing, maybe catching a fly sometimes. And the young Kung Fu guy has a like huge problem. So but the master speaks Chinese. So the function is a translation. So the young Kung Fu guy says, "Oh master, I have this TSP traveling salesman problem with 100 cities, and I don't know if I can do it under the cost of 1,000. And he has to use the function that somehow translates it to Chinese, and then the master either says yes or no. And that's how reductions work. So you have to maintain the answer. Okay. This introduces, so if a problem reduces, if problem A reduces to B, it means that the problem B is at least as hard as the problem A. And a problem is NP-complete if all problems in NP reduce to it. If you never saw an NP-complete problem, this sounds like magic. But it's possible to find a single problem in NP. For example, the set cover problem I showed you, or the traveling salesman problem, or hundreds and hundreds, hundreds upon other problems, that all the difficulty of guessing and doing polynomial time computation deterministically is captured by simply solving their instances. So it's enough that we take some known NP-complete problem, and if we can reduce it to our problem, it means that our problem is at least as hard as everything of NP. And then it's believed that it is strong evidence that the problem is hard. Okay, I see you're at least satisfied with, or at least you're willing to nod.
I'm rather, yeah, amazed. Yeah.
Yes? Okay, so is there someone who wants to ask a question? Or is there, so again, the rule of thumb is that if you're sitting in a class and you don't understand something, it means at least half of the people also don't understand the same thing. Which means you probably can ask and it's fine. Except it's recorded, but I mean, I'm joking. Other thing is, if I remember correctly, it is Saturday. It is Saturday evening. You came to a class. If you're sitting here and you're not understanding, there's something wrong. You should ask a question. Okay. So coming back, of course, if you want to ask a question, please do it. So as I told you, winner determination, for most single winner rules, it's polynomial time. But actually, there is a rule for which it is NP-complete, or NP-hard at least. So okay, I sometimes will say NP-hard and sometimes NP-complete. So being NP-complete means I'm in NP and every problem in NP reduces to me. Being NP-hard simply means every problem in NP reduces to me. So NP-hard is potentially harder than NP. Okay.
So what would be helpful is an example of a proof if it is feasible, or in intuition, how do you usually show these results?
Coming. Okay. So I will exactly show you a reduction now. So, but first I have to explain the problem. So we're dealing with rule from Charles Dodgson. Okay, how many people here heard of Charles Dodgson? 1, 2, 3, 3.5. In fact, I claim that it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, over 20. I claim that more than 20 of you have heard of Charles Dodgson, because he's better known under his name Lewis Carroll, the author of the Alice in Wonderland. The guy was a mathematician, and aside from apparently doing strange things with little girls on a boat, he was actually doing relatively good mathematics. And in particular, he came up with a voting rule. And he said the Dodgson score of candidate C is the smallest numbers of swaps of adjacent candidates that ensure that candidate C is a Condorcet winner. So here we have an election, which we can see most of. And in particular, this is the same election that we have seen in the introductory slide. It has this majority graph. So here, green defeating red means majority of voters prefer green to red. So Dodgson's score of green is 0. She is a Dodgson winner. She's also a Condorcet winner because, well, you don't have to do anything to make her a Condorcet winner. However, if you look at the red guy, what is his Dodgson score? Well, let's see. The red guy is already majority preferred to everyone except for the green lady. So here there are 4 votes, 2 votes where red is better than green and 4 votes where green is better than red. So if we look at these 2 votes, for example, why not? And if we move red forward, then now he has 4 votes to 2 against the green lady. So he's defeating her, and of course nothing changed with the others. So his Dodgson score is 2. Okay, so our problem, our decision problem right now is to find out if how many swaps are needed to make someone a Condorcet winner. And in the decision variant of the problem, we're essentially saying, here is a number of swaps you're allowed to make. Can you make a given guy a Condorcet winner? Okay, is the definition of the problem clear? Because now, okay, so in these lectures, occasionally we will do some proof. And for the proof, so essentially, I will somehow warn you when I'm doing a proof, and this is the moment. So essentially, either stay focused for some period of time to understand the proof, or you have a break, depending on your attitude. Okay, so there's actually a bunch of papers on these problems. It's in particular, this particular problem is NP-complete. The problem of deciding if a given guy is a Dodgson winner is even harder than NP.
What kind of swaps were allowed? Just neighbors? Or?
Yes, only neighbors. So you can essentially you could swap a red guy with the green lady. If for some reason he was also missing votes against the pink lady, you could swap him again. But essentially each push forward, because you can realize that probably the only thing that matters is pushing your guy forward. So you're asking for that. Okay. Now Dodgson's score is NP-complete. And we will do reduction from a problem called X3C, which is essentially the set cover problem we have already seen before. The only difference compared to set cover problem is that every set contains exactly 3 elements, which in fact happens to be exactly the instance that I showed you before. So the way a reduction works, yeah?
Could you please explain the problem again, the set?
Okay, sure. So what we have is, so I'll do it with the X3C version. And I was going to say I lost the chalk, but I do have it. Okay, so the problem, so I guess you want the problem that we reduce from. Mm-hmm. Yep, okay. So problem. By the way, this format of specifying problem is problem, data, and question. This was, I think it was first used in Gary Johnson textbook on NP-completeness. The title of the book is Computers and Intractability. So the first proof of NP-completeness of a natural problem was in 1972, I believe. It was Stephen Cook showing that the problem of satisfiability for Boolean formulas is NP-complete. Computers and Intractability, the first textbook was from '79. So 7 years. In the meantime, probably definitely more than 100, and probably hundreds upon hundreds problems were shown NP-complete. It was enough to write probably the best textbooks explaining the notion of NP-completeness. It was also somehow amusing at times, because in that textbook there was somehow a motivating example, why is NP-completeness important? So there was a cartoon and there was a programmer in a company saying, sorry boss, I can't solve this problem, I guess I'm just too dumb. And Gary and Johnson wrote, but when you learn NP-completeness, you can prove it's NP-complete, and then you say, sorry boss, I can't solve this problem, but these famous people can't either, so don't fire me. Okay, the problem is X3C. Data, so the input, is we have some universe of elements. In this case, it will be U1 through U3k. k. So this is a special, so this k is actually part of the input as well. Actually, it's part of the input because from the number of elements here. So we are assuming that the number of items to cover is a multiple of 3. Okay? And we have a family of sets S1 through Sn. And for all I, Si is of size 3. Okay, so in this slide, you see that we have 1, 2, 3, 4, 5, 6. So k equals 2. 2 times 3 is 6. And we have a bunch of sets, each of 3 elements. Right? And the question is, is there set I of indices from 1 to n such that, and first of all, I contains exactly k elements, and note, okay, exactly k elements, and the union of sets with indices from I, Si, is exactly the universe. Okay, so is the definition clear? So, but there's one important thing here. Since we have 3k, we have 3k elements, and we can use only k sets, and each of them is of size 3. It means that each element belongs exactly to one set that we use. So this name X3C, it means exact cover by sets of 3 elements. Okay?
Is this a relevant problem?
Is this a relevant problem? It's an NP-complete problem.
Yeah, it just seems artificial.
Yes, it is artificial because it was made to be artificial. Because essentially this problem exists exactly so proofs are easy. When you do reductions, maybe I can use another board. So I'll show a small diagram. Okay. So there's, so the first ever problem that was shown NP-complete is known as SAT. It's a problem where you're given a logical formula, and you're asked if there's a setting of variables that satisfies this formula that makes it true. Okay? And you could also think of it that you're given a Boolean circuit, so a bunch of electronic digital electronics devices, such as if you put some input, some signal 0, 1, 0, 1, 0, 1, on the input, is there a way that this signal translates to 1? So this problem, this NP-complete problem, essentially captures the whole non-deterministic computation. Okay, are you willing to accept that much? Okay, so then there was a bunch of problems that were shown to reduce, so that SAT reduces to them. So for example, it's relatively easy to show that independent set is NP-complete, and independent set is a problem where you're given a graph, and you ask if you can choose at least this many vertices where there's no connections between them. So for example, can you choose a group of people that neither of them is a pair of friends, so that makes some decision, why not? And this is almost the same as the vertex cover problem. Vertex cover. So vertex cover is you're given a graph, and you ask, can I choose up to k vertices so that every edge is touching a chosen vertex? So for example, you're putting security guards in some location, and each vertex is a place where a security guard can stand. Each edge is a place where he can be looking, which he can be guarding. You're asking, can I guard the whole area with k guards? And in particular, vertex cover, there was actually going in a different order. It's almost like set cover. So set cover is almost the same like our problem, except that in vertex cover it was about edges and vertices. In set cover, you have this universe, you have the sets, and K is not taken from here, but K is external. And one interpretation of this is as follows. This is a set of, say, skills that you can have. Say you're forming a team, and the team should represent each of these skills, and the sets are actually people. Each of them has some skills, and you want to find this, say, a team of a given size with given skills. Okay? And then, if you're careful enough, you can reduce to X3C. And here, X3C is exactly as you said. This is an artificial problem. And the only reason it was made was that a lot of proofs follow by reduction from set cover. And it's useful to make it. But it's unpleasant because set cover has somehow, these sets can have different sizes, things can happen. So someone actually decided, okay, let's see what's the kind of smallest fragment of set cover that still remains NP-complete because it's easy to make reductions. Okay. So again, either you're satisfied, or you learned more than you wished, or this is kind of explanation by threatening. You can either accept, or I will keep explaining. So which one? Very good. Okay. So we're going to reduce from X3C. So essentially, when you give a reduction, you have to give an algorithm for computing this function that translates the problem. So this is so most of the proofs I will be giving to you, they're somehow semi-formal. So I'm somehow working on a picture, but it will be possible to generalize the idea. Okay. So on one hand, I have the X3C instance. I have to make an election and a candidate that I want to check if can become a Dodgson winner. Okay, so my set of candidates this time will be 1, 2, 3K. So this is the same 3K as here. And in our picture, it would be 1, 2, 3, 4, 5, 6. And these are somehow the element candidates. Then I have their clones of elements. So every element comes in the real variant and the prime variant that exists only because it's needed for the construction. Then every set will be a candidate as well. And finally, I have a candidate P, and I will be asking if he can be made a Condorcet winner by a given number of swaps. Okay? And then I have this set of candidates. I have to prepare votes. So my first votes, I call them X3C votes. They will be modeling exactly this instance. So for set S1, which is blue, you can barely see it, but it is blue. It is 1, 3, 4. So it is 1, 3, 4, set 1. My guy, and then whatever follows in whatever random order, because it doesn't matter. I will only be pushing P forward. So for the yellow set, 1, 3, 6. For the 2, 4, 5 is green. This is apparently green, and so on. Okay? Actually, I need a volunteer. I need someone who will suffer through this proof with me. Someone who actually wants to understand and who will answer my questions. It seems that you just volunteered, right? He asked you, do you want to be one? And you said no, so.
Very observant.
Yes. So are you willing to be one? Can you speak?
Little bit.
A little bit, good. That means if the only word you can say is yes, is great, because I will only ask, do you understand? Yes, yes. Okay, very good. But don't worry, it's not a problem. Okay, so we can have votes like that. So it's clear how, so far I have to show you all the votes before you can actually understand the proof, but now is it clear that I defined?
The tie breaking is by...
there will be no tie breaking. Yeah.
Is it just an example?
This is more or less a proof.
I mean, are these relationships built upon the picture, or
so this is built upon the picture, but the way I'm building these things is that if I have a set with, so essentially I put the elements of a set, the set itself, and then my candidate P. I do it for every set. So I will have, if there are, like in this case, if there are n sets, I will have n votes here. Okay? Do you accept?
What about the order?
It's irrelevant. So I can sort them here by number, whatever. But it actually, for the proof, it will be irrelevant. Okay, then I will have something called equalizing votes, which are only of the form a real candidate, his clone, then P, and then whatever else. And I ensure that every set element is preferred to P in the same number of votes. So here I'm saying set element. So each of these guys, 1, 2, 3, 4, 5, up to 3K, sometimes comes in front of P in these votes. Sometimes he comes below. So by the equalizing voters, I mean that I put enough of them for each of them, so that there's always, so 1 comes before P the same number of times, 2 comes before P the same number of times, 3, 4, whatever, they come before P the same number of times. So if there were n votes here, in the worst case, there will be n times 3k votes here. Because for every candidate, I have to at most add n voters. Okay? So, are you willing to accept?
Yes.
Yes. Are you willing to accept because you understand? No. Okay. Okay, so no, but we can try to. I guess if I draw here, it won't help you much. I can.
You can put this up, yes. This.
Oh yes, good point. Apparently, I can put it up, but it doesn't help. Okay. Still more.
What is P?
So P is a special candidate. I will be interested in his Dodgson score.
Okay. One of them, or is it arbitrary candidate?
No, it's an extra guy. So I have 3k of these, 3k of these, n of these. So I have 6k plus n plus 1 candidates. Okay. So let's say that the X3C votes.
And which letter do you use in other countries?
Excuse me?
Which letter do you use in other countries?
Well, I always use P, in fact, because so my name is Piotr. It does not stand for Piotr. It stands for P, the preferred candidate I care about.
Okay.
By accident only P. But I promote this choice. Okay, so we have some X3C votes. So for example, we can have, let's say we have only like 1, 2, 3, 4 S1. And let's say that then we can have, and here's something, then we can have, for example, 1, 2, 4 S2. This is another example. It's not related to what's there. Then we can have maybe 4, 5, 6 S3. So this actually will be a no instance of X3C, because we have 3 sets, and you cannot choose 2 of them, say, that will together give the full thing, but it doesn't matter. We're doing just an example. So let's say these are our X3C votes. Okay? And if you look at, oh, there was P as well in the, there was P here. Okay? And now you can see that the guy 1 was before P once, twice, and that's it. 1 was in front of P 2 times. But 3 was once, not here, not here. So 1 was twice before P, but 3 was there only once. So I am adding equalizing vote for 3. So I'm doing 3 better than 3 prime, better than P. Okay. Now candidate 2, he was also only once. So I put an equalizing vote for 2. 3 was handled already. 4 is here. Oh, 4 is actually 3 times. So in fact, the highest number is 4. So in fact, I need to make sure that everyone there is 3 times, which means I have to have another equalizing vote for 3, another equalizing vote for 2, and in fact, I need an equalizing vote for 1, but only one of them. Okay, so 4, then 5 was 2 times, so I would need 1 more, and 6 is 1, so I would need 2 more. So is now the purpose of equalizing voters clear? Okay. So at this point, we know that each set element is the same number of times before P. Now I'm adding another group of voters, which I call defeating voters. And here their role is to ensure that for each set element we have, so this is notation I have not explained, but I have to say that. So this is actually the number of times that I is before P, number of times that P is before I. So essentially, so I made sure, with equalizing voters, I made sure that each of these guys was in front of P a given number of times. But probably P is still better than most of them most of the time, than all of them. So I add enough votes where the element guys are in front of P. I add enough of them so that each of these elements has just one vote of advantage over P. Okay? Now I could also add some voters that, for example, would ensure that P is better than each of these guys, that he is better than each of these guys, and he's only losing to these guys by one vote. Frankly, I don't actually need to do it because if you check carefully, it is guaranteed by itself. But if you don't believe me, you can add such voters. Then, again, play with the equalizing voters a bit and you have it.
So
okay?
This is your final condition that you were building?
Yes, 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 yes. So essentially, so I care about these votes, and these votes exist only so that P is defeating everyone except for these guys up to 3k, and this up to 3k, he's only losing by one vote each. Okay? So are you happy as well? Or no? Do you want to be happy?
Maybe.
Okay. So again, we had this election here, and
5 and 6.
do you want me to put 5 and 6 as well?
We should also put that.
Yes, 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 we should. I only stopped because I was lazy. So can I not? Or okay, okay. So if you look at this, P, so S1 is better than P once, and in every other vote, P is better than S1, which means that P will actually, and in these votes, P is better than S1 as well, which means that in the whole election, there's only one vote where P is worse than S1. So P definitely has has advantage over S1. Okay? Now, only in these votes the prime guys appear. So we can somehow expect that. So here there's n votes here, but in fact, of each group here has less than n voters. Because if there was some candidate that appeared in every set, then it would be immediately a no instance of X3C. So each of these groups has less than n voters. Sure. Why not? We can write correctly. Okay. So the prime guy is always behind P here, the 3' guy. But here in less than n votes, he's in front of P. And in all these guys, he's also behind P. So it means that definitely P is better than each of the primed guys, right? However, now here 3 is better than P at most n minus 1 times, but all in all, this will be, so each of these guys, like the 3, he will be, so here we have actually n votes, but this is simply a coincidence because we had this guy 4 that appeared in every set. So this is an immediate sign that this is a no instance. So if it doesn't actually happen, then we will have fewer than for each candidate that appears here, there will be fewer than n votes where he appears before P. And in fact, there's also lots of other votes where for example, this 4 guy appears after P. So all in all, P is actually doing very well in this election. So he's before we add the defeating voters, P is actually defeating everyone. Okay, and we also know that he's defeating the guys 1, 2, 3k, the regular elements, by the same in the same number of votes. Maybe different votes, but the same number. Okay, so now let's say that altogether there was I don't know, let's say 1,000 votes, and in 300 of them, the element guys are better than P. Okay, so if we add one vote like this, then we will have 1,001 voters, and in 301 they will be better than him. Okay, so now I'm not sure how many I have to add, but let's say if I add 600 votes like this, this will be probably maybe too much. I'll add 400. If I add 400 votes like of this form, then here I will add 400 as well, and now I have 1,400 votes, of which 700 prefer element guys to P. So we're now exactly at equal terms. Now I add one more. So I have 1,401, of which 401 prefer my element guys, which means that I have the smallest majority possible for these guys. Okay?
Yes.
Yes. So this is what I achieve here. So is it now clear?
Yes.
Okay. And now we're nearly done with the proof.
But for some I could be more than one. Right?
No, it cannot be, because I have equalizing voters. So I made sure that they all have the same, they all are the same number of times in front of P and the same number of times behind P. So that's why I can deal with all of them here at the same time. Okay? And now I claim, so P defeats everyone except for the set elements, because this was exactly what we did. And I claim that P has Dodgson score 4K if and only if there is an exact cover. Now, of course, I have to show that this is the case. And if there is a vertex cover, so let's, I don't have an example here, but okay, you can see that in the X3C votes, P is 4, to make P go in front each of these guys 1, 3, 4. So I can make 4 shifts to get him in front of 3 elements. Okay? That's clear, right? If I push forward P by 4 positions, by 4 moves, I get to defeat 3 guys. Right? But in every other vote, here, by pushing for 2 positions, I get only 1 guy. So here the value of a swap is somehow 1/2. Here, to reach the actual real elements, I have to pass all the clones. So in the best case, if I push P to the front, so for making 3K swaps, actually for making 6K swaps, I can only get 3K guys. So again, each swap on the average gives me only half of the guys, whereas here, each swap gives me somehow 3/4. So it's clear that if I can make only 4K swaps, of course I cannot do them here because I will have even lower benefit. I have to make them in the X3C votes. And for each set, I actually have to make exactly 4 movements to pass the set and its contents. And to make sure that I pass everyone, because I have to pass each of them once, I have to find exactly the cover. So for example, in this case, I would have to do 1, 3, 6. So 1, 3, 6 here, and 2, 4, 5, well, and 2, 4, 5 here. Okay? So this is essentially a correct proof. So again, actually you're one of the best person I can have for asking for these things, because you're willing to say when you need more. So that's actually very good. So are we okay or?
Yes, okay.
Okay, very good. You're relieved of your duties, and
Excuse me,
sure.
could you repeat what the exact cover is?
Sure. So, okay. These are actually slides I often show to PhD students and to scientists. So I somehow skip on some details sometimes. So exact cover in the X3C, we said that.
That's the same thing.
Yeah. We have 3K guys. So by exact cover, I mean we're choosing K sets that cover 3K elements. Each of them is of size 3. So each set we chose, it cannot have intersection with the others. So by exact cover means I'm choosing sets that cover everything and they don't have intersection. Sure. Okay, so we're done with this proof, and we're happy that most of the time winner determination is actually polynomial time. And there's also a number of other problems that show up around winner determination, such as possible and necessary winners, which means, for example, if you have only partial data about the preferences, can you somehow fill in this data so that someone becomes a winner? Or do you know that irrespective of how others vote, a given guy actually is a winner? You can try to have problems of winner prediction, so you can have some probability of each vote showing up. And there's a problem called,
excuse me, where can you find this previous proof in literature?
Going back.
Dodson is indifferent.
Yes. So the original proof was Bartoldi-Tovian trick, voting scheme for which it can be difficult.
Your proof on the slides.
Oh, well then it's.
Where can you find the literature?
Yeah. So I mean, the proof I show is from this paper. I guess I can make my slides available as well. But I think there's probably a number of papers that do exposition of this proof. So here in 1989, this proof was shown. It was shown to be the problem. The Dodson score problem is NP complete, and that's where it was shown there. And they also shown that the problem of deciding. So you're given a question: is this candidate P a Dodson winner? So the fact that you can, computing the score is different from saying who is a winner, because you're only asked if a given person has a given score, but you're not asking if others have lower scores. But if you're asking if, or higher in this case. But in the winner problem, you can ask, is this candidate one with the lowest Dodson score? So as opposed to other rules here, we want the score to be lowest. So they showed that the winner determination is actually NP hard. And only, what, 89, 99, only 8 years later, Lane Hamaspander, Edith Hamaspander, and Jörg Grotta had shown that the problem is actually, it is complete for a class known as NP with log n access to NP. So P with NP, I have to write it, sorry. The class is known as P with access to NP oracle log n times. So in other words, if someone magically allowed you to solve log n NP complete problems, then you could solve the winner problem for Dodson in polynomial time. So it's a class of problems that are much harder than NP itself. And it was, in fact, it was the first natural problem for this class, P and P log n. So it was actually a big deal that these guys managed to show it. And it also explains why I'm doing computational social choice, because this guy, Lane Hamaspander, was my PhD advisor. And then a bunch of people studied the problem in various ways, approximations and all sorts of things, but we will actually not go into that more. Okay. So through the proof. So there's a bunch of problems related to determining winners. There's also another set of problems. And I guess we're slowly reaching somehow the end of the first session. So we will probably mostly focus on this one puzzle. And then, as dangerous as this to say, half of the next lecture, or even more, will be a single proof. But an exciting one. So if for some reason it was appealing for you to come to a class on Saturday and staying for a really good proof, wow, this is so much better. It's like, I don't know, getting free drinks in a club. The effect might be the same. So we have the following puzzle. We're voting for an operating system to use in the lab. Let's say that these are the votes. So 7 votes say Linux is better than Windows than Mac. 6 votes say Windows is better than Linux than Mac. 2 votes Mac, Windows, Linux. 1 vote Mac, Linux, Windows. Okay, first question before you see the voting rule. Which operating system do you think will win?
Mac.
Very good. If we use Borda rule, then the scores are 21, 20, and 5. But in fact, the question is, why will the Mac win anyway? Your answer is actually correct.
You're asking me?
No. I'm simply saying that your guess that obviously in such a situation Mac should win is correct. And in fact, I have to say, okay, so I've run this experiment. I was teaching a class on algorithm game theory on Thursday. So I gave the students so each student received a piece of paper with his preferences. So each of them got the preferences. Yeah, that's how democracy works. You're just told what you believe. But and their goal, they were told that they're using Borda. And their goal was to ensure that they get as good result as possible. And I didn't tell them what others had preferences, but I told them that there was 7 for Linux, 6 for Windows, 3 for Mac. And the result was that Mac won. Why?
Because they mistook the order of border.
No. You mean mistook the order of...
So they put 0, 1, and 2, and not 2, 1, 0.
No, that was not a problem, no. No, they knew what they were doing. They were students, but still.
So can you recall what is border?
Yeah, so Borda puts 0 points here, 1 point on the second, 2 points on the first. So if they cast exactly these votes, Linux would win with 21 points, Windows would get 20 points, Mac would have 5 points. Of course, they were allowed to cast whatever votes they wanted. Yes?
Is it because Linux and Windows were kind of its war and not one company?
Exactly.
Can you please say it again? I did not recognize.
So
Okay.
Linux and Windows are its war. They have a lot of guys for them, and Mac is kind of compromising in no ways.
Then not exactly. But indeed, Linux and Windows here at war. So if you're a smart Windows voter, these Linux things, they win. No way. I'm putting Mac forward. I don't like it, but it's not winning. So I can move Mac a bit forward. I take 1 point away from Linux. I give 1 point to Mac, but Windows wins. Because indeed, if one person did this, the Linux would get 20 points, Windows would get 21, Mac would get 6. But another Linux user said, I do the same. I put Mac forward. And in fact, if all these guys manipulate and move Mac before Windows, move Mac before Linux, and if all the Mac guys are peaceful enough to just simply stay at what they are, in this election, then Mac wins. So if everyone tries to manipulate the election, and each of them is actually acting rational, from the point of view of each of them, it's a rational decision. In the end, the least popular option wins. So strategic voting like this is not only it's possible under this rule, but it can actually make that the least popular candidate wins. And the question that we will be answering after the break is, can we avoid such strategic voting? So to give away what we'll be proving is that if you want your rule to not be a dictatorship, so a rule is a dictatorship if it simply does whatever a given specified voter says. So for example, actually no examples. I wanted to say I'm a dictator in this class because if I say we do approve, we do approve. But okay, so we want a rule that is not a dictatorship, so that sometimes it does something else than what a given guy does. If it's unrestricted domain, so you're allowed to cast any single vote that you like. So every preference order is allowed. And if you want the basic property of unanimity, so you're saying that if everyone thinks that I should be the president, then I get to be the president. So if you put these 3 conditions, then we get what is known as Gibbard-Satterthwaite theorem, which says that if you have a set of at least 3 candidates, then dictatorship is the only social choice function, which means here you have a preference profile. And okay, this is one moment where we're actually dealing, the proof is much easier if we're dealing with rules that actually produce a single outcome. So here we're assuming that tie breaking is done within the rule. So if you have a preference profile and a function that produces you a single winner, so if each vote is possible, the rule is unanimous, and you want reporting the preferences to be the dominant strategy so that you can never benefit from reporting a different preference order than your original one, then the only possibility is that it's a dictatorship. Because if it's a dictatorship, it's perfectly okay to say what you think because it doesn't matter. And this is the only rule. Of course, in some dictatorships, it seems to be actually the other way around. But, of course, this is actually an extremely strong theorem. It says every single voting rule that is ever used in any reasonable democracy creates motivation to lie and to misrepresent votes. It's impossible to avoid that. And we will prove it next time. To show just how popular a theorem it is among economists, the original proof was from Gibbard in 73, independently by Statterwhite 75, then Schneider, Sonnenschein 78, Barbera 83, Barbera Plague 90, Benoit 2000, Sen 2001, Remy 2001, Kato 2009, Ninja Batman 2012. And we will be using the proof of Benoit because it's the simplest. Of course, many of these proofs were actually somehow doing other things in between. But if there's one true theorem in economics, this is it.